Figures 13.8 through 13.10 demonstrating polymorphism by invoking a derived class virtual function via a base class pointer to a derived class object. Now, earlier in this lesson, we took a look at an example in which we took a base class pointer and aimed it at a base class object and then called a function through that pointer. We then demonstrated taking a derived class pointer, aiming it at a derived class object, and called a member function through that pointer. And finally, we took a base class pointer and aimed it at a derived class object, and then called the same print function through that pointer. And when we took the base class pointer and aimed it at the derived class object, we saw that the base class version of the print function was called, and we did not get the extra information about a base plus commission employee as part of that output. Well, we're now going to revisit that same basic example, but we've slightly modified the commission employee and base plus commission employee classes in this example. And the only modification is for our print and earnings functions. We've declared them with the keyword virtual. Basically, once you declare in a class header file in the declaration of a member function that the function is a virtual function, that tells the compiler that it should no longer statically bind the function calls to the pointers and potentially to references as well. So basically it's saying the type of this object is going to potentially be changing over time at runtime, and I want to delay the decision on which version of earnings to call and which version of print to call based on the type of the actual object that the pointer points to, rather than based on the compile time type of the pointer itself. So we declared these two functions virtual. By the way, when you do that, you do not need to change anything at all about the implementation of those two member functions. So it's just in the header file where we declare the virtual keyword for these functions. And once you declare these functions virtual in the base class, every single function that has the same signature throughout the rest of the hierarchy is automatically virtual, but as a good programming practice, we went ahead and declared the versions in base plus commission employee as virtual as well. Now I want to emphasize the fact that in commission employee, earnings takes no parameters, returns double, and is a const member function. And exactly the same inside of base plus commission employee, earnings takes no parameters, returns double, and is a const member function. Similarly, if you look at the print header, print takes no parameters, returns void, and is a const member function. And same thing here in base plus commission employee's header file as well. When you want to redefine a member function to work differently in a derived class, which is more formally called overriding the member function definition, it's extremely important that you use exactly the same signature as the version in the base class, because if you don't use the same signature, then it's not considered to be overriding the original member function definition. And in order to do polymorphism, the functions need to be able to be called exactly the same way. So that's what we're going to be demonstrating here and in the next couple of examples as well. Now, if you look at figure 13.10, and if you study the code in this figure, what you're going to see is that it actually is the exact same code that we discussed in the very first example of this chapter. But I'm going to go through it all in detail again so that we can talk about these static and dynamic binding concepts for the decisions as to when a particular function will be bound to a pointer or object, and then separately we want to see what the output looks like as well. And I have already executed this, so here's the output of the program, and we'll look at that as we go. So back in main, we've created here a commission employee object, Sue Jones, and again a pointer of type commission employee that's currently a null pointer, and the Bob Lewis base plus commission employee and a base plus commission employee pointer as well, also a null pointer. Now, just like we did before, we're going to first output the contents of these two objects. Now, when you use the object's name to invoke a function, the object's name always represents the object of the particular type that was declared. So it's the variable commission employee was declared to be a commission employee capital C object. And therefore, at compile time, the compiler knows this is a commission employee object and it knows what print function needs to be called. So this is actually an example of static binding. In C++, if it knows everything it needs to at compile time, it's going to bind the function to the object at compile time because there's actually a little bit of extra overhead associated with runtime dynamic binding, and therefore C++, which is a language that tends to be geared towards performance, is going to try to help you at the compiler level to prevent using extra overhead where it's unnecessary. So anyway, this is going to be a statically bound print function call on our commission employee object. And similarly at line 39, we know precisely what type of object we're dealing with, which means we know exactly which print function needs to be called here. So this too will be statically bound by the compiler. And if we stop there and look at the beginning of the output, just like before, we see our two objects, one commission employee, one base plus commission employee, and we see all of the data for each of those objects. Now, let's continue to line 46, where we have the commission employee pointer aimed at a commission employee object. So we have a base class pointer aimed at a base class object. Now the problem is, once you have virtual functions, there is no way to tell for sure that this variable will definitively be aimed at a commission employee object at all times in our program. So now this is actually a dynamically bound function call. At runtime, it's going to look at the type of the object that this pointer points to and then use that object's class's version of the print function. Now at compile time, it's still going to look at the type of this pointer to see if you're allowed to call print through a commission employee pointer. So it's going to first go to class commission employee and see if there's a print function that takes no parameters, which of course there is. So the compiler allows this to compile. Then when we run this program, it calls the print function for whatever this pointer is currently pointing to, which is of course the commission employee object, Sue Jones. So if we stop there, you can see that we output the commission employee object, Sue Jones, just as we had done up above. Next, we deal with derived class pointers and objects. Here we have a derived class base plus commission employee pointer being assigned the address of a base plus commission employee derived class object. And of course you can always aim a pointer of a given type at an object of the same type, which is what we're doing here. So again, when the compiler looks at this, because print is now a virtual function, it is conceivable that this pointer could point to some type of object that's not a base plus commission employee object. That would of course mean that we have derived from this class another class that is where that class has the is-a relationship with class base plus commission employee. But this is actually going to be a dynamically bound function call as well. But at runtime, we know this is aimed at a base plus commission employee object. Therefore, the print function that gets called will be the base plus commission employee's print function. And if we stop there for a moment, you can see Bob Lewis being output. And you can compare the output with what happened up above to make sure that it is indeed correct. Now, here's where we get to the interesting part. At line 60, we take the base class pointer, just like we did in the first program in this lesson, and we aim it at a derived class object, the base plus commission employee. And just like before, when the compiler encounters what is now line 67, it's going to look at the type of the pointer to see if there's a print function in that class type that takes no parameters. And of course, class commission employee does have such a print function. But at runtime now, because print is a virtual function, is when the decision is going to be made as to which print function to call. And this is an example of polymorphism here. When we call print now, we're going to get the full set of base plus commission employee information, whereas if you go back and look at the output from the first program in this lesson, you'll see that we only get the commission employee part of the base plus commission employee object. So if you take a look at the output here, you can see that even though we're calling print through a commission employee pointer, what we're actually getting is the base plus commission employee version of print getting called, and you see the words base salaried at the beginning and the base salary information at the end. So in the next lesson, we're going to take a look at this polymorphism concept in much more detail with an employee class hierarchy that will allow us to do polymorphic payroll calculations.